Good morning. Well, here we are on a beautiful Pacific Northwest day. Sky is blue, can't see a single cloud, so I've decided to move myself outside. All of the ski resorts are closed, so I can't do what I did yesterday, and if you like skiing, I'm very sad for you. I'm very sad for me as well. So it gives me an opportunity to start looking at how we're going to cover what we were going to cover anyway, which is organic chemistry. So organic chemistry looks at the idea of molecules based on carbon, often very long chains of carbon, and the basic type of those is called an alkane. So the alkanes we've looked at quite a bit already, just incidentally, because we've had to look at the combustion of methane and ethane and so forth, and try and balance enormously complex combustion equations for those. But we need to do that formally now, and we need to look at the way that organic molecules are represented in diagrammatical form, and we also look at how we need to name those properly using the IPAC designations, the official internationally agreed system of naming organic compounds. So let's have a look at these. We're going to start with alkanes. Alkanes are basically hydrocarbons made only of hydrogen and carbon, and they have only single bonds in them. As you know, carbon can form 4 bonds because it has its 4 electrons in its outer energy level, 4 valence electrons, and so therefore it's likely to form 4 covalent bonds. And hydrogen has only 1 electron of any kind, and so it tends to form 1 covalent bond. And either way, what happens if carbon forms its 4 covalent bonds and oxygen its 1, then what happens is they tend to complete their octet, and therefore achieve some kind of chemical stability. And so this is what they're likely to do. And the alkanes are the easiest way of doing that. So the simplest alkane, methane. So methane, a very familiar kind of name for you, and something you use quite a lot in Bunsen burners, and it's represented by this fairly simple formula. Now obviously that's not how it really is, it's how we tend to represent it on a two-dimensional structure like a piece of paper or my daughter's whiteboard here. What you need to know is, of course, that this is a three-dimensional structure. It has these 4 electron clouds and they repel each other. And because they're identical, and the reason they're identical is each one of them is a pair of electrons. One of the electrons comes from the carbon and one from the particular hydrogen that's forming the bond, and these identical clouds will repel each other identically, and that results in an angle of around about 109.5 degrees. And so drawing 90-degree angles everywhere, it's easy to do, it's recognizable, and it's very clear, but it's not very accurate. And so what we look at now will be a kind of diagram that is maybe a little accurate, but mostly one that is simple and clears the way for when we have to add all the functional groups that we'll look at in videos after this one. So let's have a look at what this name is. It's 2 parts. The prefix is the number, and that of course is 1. There's 1 carbon there. And the ane simply means it's in the alkane family, and the alkane family means that there are no double bonds. These are all single bonds between the carbons, and with the hydrogens, because hydrogens are incapable of forming anything other than a single covalent bond. So I think you know most of these at the start, so let's do them quickly. 2 carbons, ethane. 3 carbons, propane. 4, bute, and the suffix is the same. 5, pentane. Well, let's stop and draw a pentane here in our old structural formula way. And here are the single covalent bonds that are formed between the carbon and the hydrogen. And here is me already getting bored with drawing hydrogens, and some of them aren't looking very H-ish. So once you get large hydrocarbons, this way of representing them is a bit of a drag, and it's a bit of a waste of time, because when you've got a hydrocarbon, when you've got an alkane, you know every carbon is going to form 4 bonds, and therefore it's going to be surrounded by hydrogen atoms. And this is called a saturated compound. And saturated means it's saturated with hydrogens. It has the maximum possible number of hydrogen atoms around it. If we had a double bond in there, for example, then that carbon would then be forming 1, 2, 3, 4, 5 bonds. It's not allowed to. It can only form 4 bonds because it's only got those 4 valence electrons. Same with this one. We'd have to do that. That's not saturated because it doesn't have the maximum number of hydrogen atoms. So let's turn it back into 1, 2, 3, 4, 5. A pileated woodpecker has just appeared in my tree. Okay, so that's a saturated hydrocarbon, it's pentane, and there's a very time-consuming and boring way of representing it. 6 would be hexane, 7 heptane, and now it's looking like drawing polygons, like hexagons and stuff. 8, as you'd expect, 9 nonane, and 10 is decane. Now we may as well go on because many of the hydrocarbons we've been using, such as those that make up candle wax, are much, much longer than a chain of 10. And so we can go into 11 is decane. 12, decane. 13, as you would expect, tridecane. 14, tetradecane. 15, pentadecane. And I've kind of run out of board there, but you get the general idea: hexadecane and heptadecane and so on. So that gives us a number of these. So now I think you're pretty well organised, maybe you were before, on how to draw alkane molecules in this way and how to name them, because that's really simple. But let's now have a look at the type of diagrams that we'll have to be meeting in future videos when we have to make much more complex molecules. Right, let's have a look at this. And we'll do hexane, simply because it's hexane. And first I'll stick that at the top. Hexane, it's an alkane. It only has single bonds between the carbon atoms, and everywhere that it can form a bond with a hydrogen atom, it does so. And that's the last one I'll be drawing of those because it's exceedingly dull. So let's have a look at another way we can represent that. We know that at the end here there's a carbon, and this carbon has 3 hydrogen atoms attached to it, a CH3 group, a methyl group, or a methyl group, depending on how you say it. And in the middle there's 1, 2, 3, 4 carbon atoms, and each of them only has 2 hydrogens attached to it, each of those, a CH2, and there's 4 of those. And at the end there's another carbon, and it's free to form 3 bonds with hydrogen atoms, and so it's CH3. So there's another way of showing hexane. 1, 2, 3, 4, 5, 6 carbon atoms, and then we can add up the hydrogen atoms also, and it's going to end up being C6H14. 3 plus 3 is 6, plus 2 lots of 4, which is 8. 6 plus 4 is 14. And then the last way of doing it, the simplest way of representing this. And I'll start by numbering. 1, 2, 3, 4, 5, 6. And that's it. That's how hexane is represented on some of the diagrams we'll be looking at in the future. And the reason we can do that is it's back to that old 109.5 degrees. And each of these is exactly 109.5 degrees because I've drawn it so perfectly, as you can see. And each of these at the end or at an angle is a carbon atom. And we can number those for reasons that you'll look at later. And we know, even though we haven't shown them, that each of these fills up all the spaces where it can form bonds with hydrogens. It's just that we don't bother about drawing those anymore because it doesn't matter. And so in future, there are many, many ways of representing hexane. There's the old, easy to understand model. There's the normal sort of molecular formula. There's a kind of shortened structural formula here where you start to see what each part is. And then finally, there's the simplest possible way of showing hexane, which is 1, 2, 3, 4, 5, 6. And there's your hexane. So at the moment, it's just a zigzaggy line. But in future, what we're going to do is we're going to add a whole lot of functional groups to that, and you'll kind of see the logic behind representing something as complex as this with something as simple as this. All right, have a good afternoon, and stay healthy. Bye-bye.